Let's start with a number that, honestly, when I first read it, I thought it had to be a typo.
Okay.
2,900 tons.
Hmm.
That is roughly what the Saturn V rocket weighed when it lifted off the pad back in, 1969 to go to the moon. It's basically a skyscraper filled with explosive liquid.
It is an absolute leviathan of a machine. I mean, the acoustic energy alone was enough to melt concrete and set grass on fire miles away. It's just staggering.
But here's the kicker, and this is the stat that really sets up everything we're talking about today.
Right.
By the time the lunar module actually touched down on the moon's surface, the whole eagle has landed moment, it weighed about 7 or 8 tons.
Which is just staggering when you do the math.
I did the math. That is a mass fraction of less than 0.25%, a quarter of 1%.
It's mind-boggling.
That means 99.75% of that massive machine was just fuel and hardware thrown into the ocean or burned up just to get that tiny little camping tent to the surface.
It's ruthless.
Yeah.
And this is what engineers call the tyranny of the rocket equation. It's the fundamental law of spaceflight. You have to burn fuel to lift the fuel that you then need to lift more fuel.
It's a vicious exponential cycle.
It is. And for 50 years, that equation has basically dictated everything we do in space. It dictates that space has to be rare, expensive, and, that the hardware has to be expendable.
But today, we are unpacking how that equation is finally, maybe, being broken. We're looking at a fascinating technical breakdown from Tim Dodd. You probably know him as the Everyday Astronaut.
Oh, yeah, he's great.
He's been documenting this huge shift from the Apollo era's throwaway culture to the new kind of insane world of SpaceX's Starship.
And Dodd really gets into the weeds here, which is what I love. We're not just talking about shiny new rockets. We are talking about a fundamental shift in physics and economics.
Exactly.
We're moving from a system where you throw away a skyscraper to fly a minivan to a system where you fly a building, land it, refill it, and then fly it again.
So let's unpack this. We have to start with the Apollo paradigm. Because looking back now, it just seems wild that we built these exquisite, handcrafted machines only to dump them in the Atlantic 5 minutes later. Why was that the plan?
It really comes down to the path of least resistance. Dodd describes Apollo as almost a stunt.
A stunt.
Now, he doesn't mean it was fake. He's very clear on that. The engineering was miraculous. But it was a stunt in terms of capability. The goal wasn't to build a sustainable shipping lane to the moon.
The goal was to get there.
The goal was to get a human there before the decade was out, by any means necessary.
Right. And the means necessary was basically brute force.
Exactly. The Saturn V was the solution to a specific problem. How do we get there with 1960s technology? And the answer was lunar orbit rendezvous, but crucially without any refueling in space.
You pack everything you need for the entire trip into one giant stack.
You launch it all at once and you just shed weight as you go.
It's like packing for a road trip from New York to LA, but you have to carry all the gas for the whole trip in a giant tank on the roof.
And not just that, you're throwing pieces of the car away as you drive to get lighter.
Right.
By the time you get to LA, you're basically arriving on a skateboard.
That is a surprisingly accurate analogy, and here's where it gets really interesting. This wasn't actually the original dream, was it?
Not at all. Dodd brings up Wernher von Braun, the architect of the Saturn V. Back in the 1950s, he was doing these specials for Disney, painting this vision of the future. And in his version, the rockets were reusable.
This blows people's minds. Reusability isn't some new Elon Musk idea.
No. Von Braun envisioned these massive winged vehicles that would fly to Earth orbit, meet up with cargo ships, refuel, and then head to the moon. It looks suspiciously like what Starship is trying to do today.
So why didn't we do that in 1969? I mean, if the guy building the rocket wanted to do it.
It was just too hard. Think about the computing power of the 1960s. Your toaster probably has more processing power today. The idea of mastering the docking of 2 massive tanks of freezing cold liquid fuel in zero gravity, or landing a rocket backward on a tail of fire, that was pure science fiction.
The Apollo computer used rope memory, right? They were literally weaving the software with copper wires.
Exactly. You physically wove the software. You couldn't run the complex fluid dynamics simulations or the real-time guidance you'd need for landing a booster. So the United States chose the expendable route because it was the only way to beat the Soviets on that timeline.
So we traded sustainability for speed.
Precisely. And that one decision locked us into a paradigm for half a century where spaceflight was exorbitantly expensive because you threw the machine away every single time.
Which brings us to the modern era, the reusability revolution. Dodd points out that the only way to beat that 0.25% mass fraction, that tiny payload, is to stop throwing the hardware away.
And you have to start with the Falcon 9.
The workhorse.
This is the rocket that changed the equation.
Dodd threw out some stats that just blew my mind. SpaceX has landed these boosters over 540 times.
Incredible.
They have a 97% success rate, and he said it's become boring.
Which is the highest compliment you can pay in aerospace. If landing a 15-story metal tube backward from space is boring, you have won.
Yeah.
But we really need to appreciate the physics of why this was so hard to master. It's not just falling with style.
Dodd mentioned something called the G-fold algorithm. What is that exactly?
So planetary landing is this terrifying math problem called convex optimization. You have a vehicle falling at supersonic speeds, getting buffeted by wind with a limited amount of fuel.
Okay.
And you need to ignite an engine at the exact millisecond so that your velocity hits zero at the exact moment your altitude hits zero.
It's a math problem you have to solve while plummeting towards the Earth.
Right. G-fold is the guidance algorithm that calculates that optimal trajectory in real time. It steers the rocket using grid fins and engine gimbals. But Falcon 9 adds a layer of difficulty that even, Mars landers don't have.
The Versland.
The hover slam. This is a thrust-to-weight ratio problem. The Falcon 9 engines, the Merlins, are just incredibly powerful. Even throttled down to their minimum setting, which is about 40%, a single engine produces more thrust than the weight of the empty booster.
So it literally cannot hover.
It cannot hover. If you light the engine 5 seconds too early, the rocket will stop in midair and then immediately shoot back up into the sky.
Wow.
If you light it 5 seconds too late, well, you make a crater.
That is terrifying. It's a suicide burn.
It effectively is. It has to be perfect. It's like trying to parallel park a dragster that can't go slower than 100 miles an hour. You have to slam the brakes at the exact right moment.
And Dodd's point is that mastering this hover slam on the Falcon 9 was the prerequisite exam. You couldn't even dream of building Starship if you hadn't proven you could solve that hundreds of times.
Exactly. They used Falcon 9 to learn how to land. And now they're applying that lesson to an absolute monster.
So let's talk about the monster, Starship. We compared the Saturn V to a skyscraper, but Starship seems to be in a different weight class entirely.
It is. It's roughly 5,000 tons when fully fueled. That is double the mass of the Saturn V. It stands 120 meters tall.
Okay, but the important number isn't the liftoff weight, right? It's what it can land on the moon.
That's the key. Remember Apollo, 7 tons.
Right, the camping tent.
Starship aims to land between 100 and 300 tons on the lunar surface.
Wait, 100 to 300? That's not a tent, that's a base.
Exactly. Dodd uses a great analogy here. He says the Apollo astronauts lived in a space the size of a minivan, about 6 cubic meters. Starship has the internal volume of half a 747.
Wow.
It's not camping, it's a condominium building. You could bring cranes, rovers, habitats, greenhouses.
And there's always a but in engineering. How do you get a building to the moon? Because the rocket equation didn't just disappear.
No, the physics hasn't changed. To get that much mass to the moon, you have to cheat the equation. And the cheat code is orbital refueling.
This goes right back to von Braun's 1950s vision.
It does. The Starship launches to low Earth orbit, and it arrives there basically running on fumes. It has used almost all of its propellant just to fight Earth's gravity well.
So it's a massive vehicle, but it's sitting in orbit with an empty tank.
Correct. So SpaceX plans to launch tanker versions of Starship, essentially flying gas stations, that meet up with the main ship in orbit. They transfer liquid oxygen and methane, top it off, and then the ship burns for the moon.
Okay, but Dodd mentions this is one of the big unproven technologies that makes critics nervous. Why is transferring gas in space so hard? I mean, we do mid-air refueling with jets all the time.
It comes down to physics. In a fighter jet, you're in gravity, so the fuel sits at the bottom of the tank where the pump is.
Sure.
We were talking about zero gravity. The fuel is just floating around in blobs mixed with gas. It's called ullage.
So if you turn on the pump, you might just suck in a bunch of gas.
Right, and if you suck a gas bubble into a high-speed turbo pump designed for liquid, the pump cavitates. It basically destroys itself. Plus, these are cryogenic propellants. We're talking super-cooled liquid oxygen and methane. If they get even slightly warm, they boil off into gas and either explode or just vent away.
So how do they solve that floating blob problem?
Dodd explains they have to use small thrusters to gently push the ship forward. This creates a tiny bit of artificial gravity, just enough to settle the fuel at the bottom of the tank so the pumps can grab it.
It sounds like a really delicate ballet.
It is the critical challenge. If they can't figure out how to transfer thousands of tons of super cold liquid in 0 G without losing it all to boil off. Starship is stuck in low Earth orbit. It goes nowhere.
So we have the landing, we have the refueling. Let's talk about the engines.
Yeah.
Because Dodd really geeks out on the difference between the Saturn V engine, the famous F1, and the new Starship engine, the Raptor.
This is a classic muscle car versus Formula One comparison.
Break that down for me. The F1 was the muscle car.
Yes. The F1 was massive, brutish, and hand-built. Dodd mentions a specific detail that I love. The cooling tubes in the nozzle were all hand-brazed.
Right.
It was an artisan process. It took months to build a single engine. And it used what's called a gas generator cycle.
Which means?
It means it takes a little bit of fuel, burns it to spin the pumps, and then just dumps that exhaust overboard. It's smoky, it's dirty, and it's wasting fuel.
That was powerful.
Immense raw power. It was the only way to get the thrust they needed with 60s metallurgy.
And the Raptor, the Ferrari.
The Raptor is the Ferrari. It uses something called full-flow staged combustion. This is kind of the holy grail of rocket engines. It was considered too hard to build in the 60s. The Soviets actually tried and failed.
Well, is this so efficient?
It doesn't waste anything. It uses all the propellant to spin the turbines, turns it into a high-pressure gas, and then feeds all of that into the main combustion chamber. Nothing is dumped overboard. Every single drop of fuel contributes to thrust.
But Dodd mentioned it's incredibly complex to keep it from, blowing up.
It is a balancing act on a knife edge. You have oxygen-rich gas spinning one turbine and fuel-rich gas spinning another. Hot, high-pressure oxygen is terrifying stuff. It basically wants to burn the metal of the engine itself.
So the materials have to be perfect.
The metallurgy, yeah. And the turbines have to spin up in perfect sync. We're talking millisecond precision, where the whole thing essentially melts or detonates. But here's the wild part. SpaceX isn't hand-brazing these. They are building a Raptor engine almost every single day.
That is the part that gets me. In the 60s, an F1 engine was this precious jewel. You built it, polished it, flew it once, and dropped it in the ocean. SpaceX is treating them like car parts off an assembly line.
And that manufacturing speed is what allows for a fleet. You can't have a fleet of Starships if it takes you 6 months to build one engine. You need to be cranking them out. That manufacturing pace is just as important as the physics.
So putting this all into context of what's happening right now with the Artemis program, I'm always a little confused by Artemis because it seems like such a mix of old and new.
That is the perfect way to describe it. It's a transitional program. Dodd explains that Artemis is currently using the SLS rocket to launch the crew. The SLS is derived from space shuttle parts.
So old school.
Very old school, cost-plus contracting, incredibly expensive, and totally expendable.
So we're still throwing away rockets to get the crew to space.
For now, yes. The crew launches on SLS in the Orion capsule, but, and here's the twist, they are supposed to dock with Starship, which serves as the lander. So you have this 1980s tech rocket meeting up with this futuristic 2020s Starship in lunar orbit.
It's a bit of a Frankenstein mission.
It is. Artemis 2 is just a flyby to test the Orion capsule. Artemis 3 is the actual landing. But there's a concern that keeps popping up in conspiracy circles that Dodd addressed, which is the Van Allen belts.
Right, the radiation belts. I've heard people say humans can't pass through them without getting cooked, so Apollo must have been fake.
Dodd shuts this down with physics. It's all about exposure time. Think of it like walking over hot coals. If you stand on them, you get burned. If you run across quickly, you're fine. The trajectory for these missions is designed to punch through the dangerous zones of the Van Allen belts very, very quickly.
So the dose isn't lethal?
Not even close. The Apollo astronauts received relatively low doses, less than a CT scan in some cases. And the Orion capsule is actually doing deep dives into the belts, specifically to test its shielding. But the physics remains the same. Limited exposure time equals manageable risk.
So, stepping back from all this, we have gone from the F1 hand-brazed muscle car to the mass-produced Raptor. We've gone from throwing away the Saturn V to catching the Starship booster. What does this actually mean for us? Why does this shift matter?
It matters because we are witnessing the transition of space exploration from being a miracle to being an industry.
Unpack that.
The Apollo era was driven by geopolitics. It was the Cold War. Cost didn't matter. Planting the flag mattered. Once the flag was planted, the money dried up because the miracle was achieved. It was flags and footprints.
Right. We went, we saw, we left.
Exactly. But what Starship represents is an economic shift. If you can reuse the vehicle, the cost of putting a ton of mass on the moon drops from billions to, maybe millions. It changes the question from can we go to what business can we build when we get there?
It stops being an expedition and starts being a supply chain.
Precisely. And that leads to the final sort of provocative thought that Dodd touched on, which I think is the key to everything.
What's that?
In situ resource utilization,
Nah.
ISRU,
Fancy way of saying mining.
making your own gas.
Yeah.
If Starship lands on Mars or the Moon, it can't carry enough fuel with it to get home. It's just too heavy.
So the plan isn't just to refuel in Earth orbit.
The plan is to turn the destination into a gas station.
You mean mining water ice?
Mining water ice from the lunar poles or from Mars. You use solar power to split the water, H2O, into hydrogen and oxygen. On Mars, you can take carbon dioxide, CO2, from the atmosphere, combine it with that hydrogen, and boom, you have methane, CH4. It's called the Sabatier reaction.
So that's why the Raptor engine runs on methane.
Exactly. The Apollo engines ran on kerosene. You can't find kerosene on Mars. You can make methane. The entire architecture of the rocket was chosen because of the chemicals available at the destination.
So if we can't do that, if we can't turn the moon into a fueling depot, then the rocket equation wins again.
Correct. We can go, but we can't stay. We'd just be tourists with a very, very expensive return ticket.
So the future of spaceflight isn't just about building better rockets. It's about becoming celestial chemical engineers.
It is. If you can't fill up the tank on the other end, you're just visiting. If you can, you're colonizing.
That is a wild thought to leave us with. From 0.25% payload to building gas stations on the moon. It's a brave new world. Thanks for diving in depth with us today.
Always a pleasure to geek out on the physics.
Catch you next time.